Assalamualaikum warahmatullahi wabarakatuh, and hello everyone. We are Group 6 from Section 2. We'll be presenting our project for Chemical Engineering Thermodynamics, lectured by Professor IR Dr. Nur Aisha Sabina Amin. So our project will be focusing on flash columns, and our title is Separation of Ethane and Propane Mixture. So this is our group members: Abdul Rahman Al-Badawi, Mohamed Khalid, Nur Aisha, and Nisa Amalia. Of our presentation video, we will start with a brief explanation of the flash separator, including its definition, purpose, and applications. Next, we will discuss the two substances involved in this project, ethane and propane, focusing on their molecular weight, boiling and melting point, as well as their industrial application. Finally, we will present calculation involved in the flash separation process to demonstrate how it works in practice. Next, let me explain what flash separation is. Flash separation is a single-stage separation process widely used in chemical industry. The main purpose of this process is to separate a feed stream into two distinct phases, which is the aqueous phase, mostly water-based or polar substances, and the organic phase, which is usually non-polar or oil-based substances. This process happens very quickly, hence the term flash is commonly used in oil refining, natural gas processing, petrochemical industry, and even in the food industry. As shown in the diagram, the fluids enter the flash vessel, and due to change in temperature or pressure, part of it is vaporized while the rest remains as a liquid. The vapor exists at the top and the liquid at the bottom. Now let's begin with ethane, which has the molecular formula C2H6. It has a molecular mass 30.7 gram per mole. The boiling point of ethane is negative 88.5 degrees Celsius, and it melts at negative 183 degrees Celsius. In terms of application, ethane is widely used in the production of plastic like polyethylene, in antifreeze, and in PVC manufacturing. Ethane is classified as more volatile, meaning it evaporates more easily. This is because it has a smaller molecular size and weaker intermolecular forces, making it easier to vaporize.
And I will be presenting some key properties of propane with the chemical formula C3H8. Firstly, propane has a molecular weight of 44.10 grams per mole. Its boiling point is around negative 42 degrees Celsius, which means it easily turns into gas at room temperature. Meanwhile, its melting point is extremely low at negative 188 Celsius. In terms of industrial application, propane is widely used as LPG or liquefied petroleum gas for cooking and heating, and also industrial heating systems. When it comes to volatility, propane is considered less volatile compared to lighter hydrocarbons like ethane. This is because propane has a longer carbon chain, which increases London dispersion forces. These are weak intermolecular forces that makes it harder for propane to vaporize compared to smaller molecules. So, due to its properties, propane plays an important role in both household and industrial energy applications. For our project, we referred to US Patent 4273566, which describes a separation process for an ethane-propane mixture. From page 4 of the patent, under the breakdown of the invention, the general feed composition is stated to be 70 to 85 mole percent ethane and 15 to 30 mole percent propane. Then, on page 7, a more specific example is given for stream 1, which is used as the initial feed, 80 mole percentage ethane and 20 mole percentage propane. It is in a fully liquid state, supplied at 80 Fahrenheit and 480 psig. This feed composition serves as the basis of our mass and energy balance calculation later in the project. For next operating condition for this project is, for consistency, we adopted the same operating conditions as given in the reference source, which are the temperature at 26.7 Celsius and the pressure is at 34.1 bar. Using these values helps us align our simulation or calculation with the reference process. It also avoids unrealistic assumptions and ensures that our result can be meaningfully compared with the actual system described in the patent. Additionally, using reference values improve the accuracy and credibility of our project findings.
Assalamu alaikum, I'm Mohamed Khalid and I'm going to present the flash calculation. So first of all, we draw the PFD diagram for the flash separator. Our basis is 1 mole of ethane propane mixture. 1 mole of ethane propane mixture enters the flash separator with 80% ethane and 20% of propane. So when the mixture enters, it enters at 26.7 degrees Celsius of outlet temperature and 34.1 bar of outlet pressure. As the mixture enters, it flashes. That means it partially vaporizes into two streams. One stream is vapor stream and the second stream is liquid stream. The vapor stream, as we know, is rich with the lighter component, which is ethane. And the liquid stream is rich with the heavier component, which is propane. Our goal is to calculate Y1, Y2 for the vapor, and X1 and X2 for the liquid, and the total number of vapor moles, which is N1, and the total number of liquid moles, which is N2. So now we are going to calculate the PSAT for each component by using the Antoine equation. But the problem is we don't have the Ant1 coefficients in our textbook, Introduction to Chemical Engineering, Thermodynamics, in both editions, 7th and 8th edition. So we brought the Ant1 coefficients from other source, which is the Yau's Handbook for Vapor Pressure, 2nd edition. So now we can calculate the Psat for each component. Starting with propane, we got that the pressure sat is equal to 766.5 mmHg. We converted it to bar. We got that it equals to 10.2 bar. We did the same thing for ethane. We got that the Psat for ethane is 43.8 bar. Secondly, we are going to calculate the dew and bubble pressure. Now we're going to calculate the dew pressure using the formula 1 over the composition of the first component dividing by its Psat plus the composition of the second component dividing by Psat. We got that the dew pressure is equal to 24.94 bar. Now we're going to calculate the bubble pressure using the formula, the composition of the first component multiplying by its Psat plus the composition of the second component multiplying by its Psat. We got that the bubble pressure is 37.08. So what's the purpose of this? We should ensure that the inlet pressure is between the bubble pressure and the dew pressure so that the flash separation can occur. So we ensure that it is in the two-phase equilibrium liquid vapor. So now the vapor stream will be rich with the more volatile component, which is ethane, and the liquid stream will be rich with the less volatile component, which is propane in our example. Furthermore, we're going to calculate the K value for each component, ethane and propane. K value is equal to the Psat for the component dividing by the inlet pressure. So first of all, we're going to calculate for ethane, which has a Psat of 43.8 divided by the inlet pressure, which is 34.1. We got that the K value is equal to 1.284. Then we are going to calculate for propane. K value for propane is equal to 10.2 divided by the inlet pressure 34.1. We got that the K value for propane is 0.299.
So now we are going to calculate the vapor and liquid moles in the outstream by using the equation 13.106 in the textbook. By set the V as unknown variable, which V in the equation means that the vapor moles in the outstream, and we have the value of Z and K for both ethane and propane. By calculating this equation, we found that Z is equal to 0.437 mole. However, the basis is 1 mole, so the rest will be the liquid moles in the outstream. So by calculate 1 minus V, we get that the liquid moles is 0.563. And then we have to find the mole fraction for both phases. For vapor phase, we use equation 13.105, and we get that the number of moles for ethane in the vapor stream is 0.914, and for propane is 0.0862. For liquid phase, we get the number of mole by using equilibrium ratio, and we found that the number of mole for ethane in the liquid phase in the liquid stream is 0.712, and for propane is 0.288. Finally, we do mass balance calculation to get the number of mole for both vapor and liquid streams, and we get the same value as our calculation with flash calculation method.
So this is the final overall PDF diagram after calculation were done, showing a flash column used to separate a 1 mole mixture of ethane and propane. The feed contains 80% ethane and 20% propane and enters the column at 26.7 Celsius and 34.1 bar. Inside the flash column, the mixture undergoes partial vaporization, resulting in two output streams. The vapor stream is 0.436 mole and is rich in ethane, containing 91.4% ethane and 6.62% propane. The liquid stream is 0.564 mole, containing 71.2% ethane and 28.8% propane. This shows that the flash column effectively separates the more volatile ethane into the vapor phase, while the less volatile propane remains mostly in the liquid phase.
In conclusion, we achieved the aim of this project is to design the flash separator for the propane-ethane mixture and also to calculate the moles of the vapor phase and liquid phase. Also, we calculated the mole fractions for all the components in the liquid and vapor phase using the Ant1 equation, Raoult's law, and Rashford-Rice equation. As a result, the result shows that ethane, being more volatile, was enriched in the vapor phase, and propane, being less volatile, was more in the liquid phase. Thank you.